All right, good afternoon, everybody. Welcome back to day 9 of Intro Physics. We are going to be picking up where we left off on Thursday. So we had just started talking about motion in 2 dimensions, so not just in a straight line, but now how we can take these kinematic equations that we had gone through and kind of apply them to various scenarios. We talked about free fall and the conditions for free fall, right? That just depends on gravity. We're ignoring air resistance. So the only force that's acting on the object in free fall is gravity. And then we had gone through a couple of examples of free fall problems. And so today we're going to finish up that example that we stopped at last time, and then kind of take what we've learned and expand it now into vertical and horizontal motion at the same time, so projectile motion. So I'm gonna go ahead and share my screen and we will get rolling. All right, can we all see example 3?
Yes.
Great. Okay, so this is the problem that we finished off with last time, where we have this ball on a roof and we are throwing it up into the air, and it is falling back down past the roof of the building, continuing down towards the ground. So part A is what we finished with last time. I just want to quickly recap what we did, and then we can continue on to part B. So in part A, we wanted to find the position and the velocity of the ball at 2 different moments in time. So 1 second and 4 seconds after leaving your hand. So we know from the problem that the ball is not dropped, right? We're giving it an upward speed, so a positive speed of 15 meters per second. And then after that is in free fall. So after it leaves your hand, there's no additional forces acting on it other than just gravity pulling it down. Okay, so here are the equations that we went through last time. Remember, we had those like 6 equations that we had in a box. Those will be handy for you to have next to you today as well. But any equations that we have written in the x direction, we can write them again in the y direction, as long as we replace everything x with everything y. Remember, x just means horizontal motion here, and y means vertical motion here. So since this ball is traveling just vertically up and then down again, we're using y. Now we put our initial height right there at the roof where our hand lets go of the ball, just for the sake of convenience. Remember, you can establish a 0 point to be wherever is most convenient. So in some cases it might be the ground, but in this case, it's more convenient to put the 0 point at the railing where your hand lets go of the ball, just because we don't have any information about how tall the building is. So then we were given our velocity, and we know our acceleration is negative 9.8 meters per second squared because it is in free fall. So a similar equation that we used on Thursday for other problems as well, our y velocity, so our final velocity at any particular moment, is the initial velocity plus that acceleration times time. So there are the equations that we were setting up. Here we plugged in our times, 1 second and 4 seconds. We got our 2 position values, 10 meters and negative 18.4 meters, and our 2 velocities, positive 5.2 meters per second and negative 24.2 meters per second. Now, we also pointed out the difference in the signs as being very important and kind of a clue as to what the motion of this object is doing, right? So if we look at time equals 1 second, we notice that both the position and the velocity are positive, right? So the ball has moved up from its starting point, and it is continuing its motion upward. The velocity is positive, so it is continuing to move upward. At 4 seconds, though, both of those are negative. So now the ball has dropped down past the railing, and it is continuing to move downward with that negative velocity. So we know that at some point between the 1 second and 4 seconds, it changed direction. It reached its maximum height and then changed directions and started falling back down. So now part B, let's find the velocity when the ball is 5 meters above the railing. So from this, we know similar things that we did for part A, right? We know the upward speed initially of 15 meters per second. It's still in free fall. We don't know what time this happens. We just know the position and we want to find the velocity. All right, so in this case, I'm going to use what we called equation 6 because that one does not involve time at all. And we don't know what time the ball is at 5 meters above the railing. So most of those other equations that we had in our box involved time in some way, and this one didn't. So that's why I chose this one. So we want to find our final velocity, which means we're looking for Vy, and here it's squared in that equation, so we'll have to take care of that at the end as well. Our initial y velocity is still 15 meters per second, so we'll square that. Plus 2, remember our acceleration in the y direction is negative 9.8 meters per second squared, because my coordinate system assumes that up is positive and gravity is pulling down, accelerating things down, so that's negative. And then the change in height that we are looking at, since we established that the height of the railing is our 0 point, that means the change in height is 5 meters. Okay, so once we add those things together, multiply and add and all that jazz, we get a answer of 127 meters squared per second squared. Now, a lot of students get tripped up here and forget that the velocity is squared in this equation, and they'll just kind of leave it at that. This is not our final answer, right? Because we haven't taken the square root yet. So here, when we take the square root, we actually get 2 different answers, one positive and one negative, right? Both positive 11.3 squared and negative 11.3 squared will equal 127. So we got 2 answers because that ball passes that height twice. Right? It passes 5 meters on its way up, so that would be a positive 11.3 meters per second velocity. And then it passes it again on its way back down, so that would be our negative 11.3 meter per second velocity. Right, so you can see one velocity is up, so positive, one velocity is down, so it's negative. And so we can have 2 different answers for this particular part. Do you guys have any questions about this? Going on.
Will you ever get the 2 answers for a ball that does not pass the time twice?
No, we would not get 2 answers for that. And part of that will be your own intuition and just kind of conceptualizing the problem correctly, right? So you see kind of the same thing with like taking the inverse tangent of angles sometimes. Like your calculator may give you 2 different answers. One is like 180 degrees more than the other. So those will just be things that you need to be aware of and really understand what is happening in the scenario, so that you can know if you get 2 answers, what that means, versus if you get 1 answer, what that means. Does that make sense?
Thank you.
Okay, so that's part B. Part C, let's find the maximum height reached and what time we get there. So in this case, we don't know what the position is, right? We're trying to find that maximum height and we don't know the time. So we can solve for one of them before the other. I mean, we can't do the same. We can't do them both at the same time, right? So we have to pick which one we want to solve for first. Now, take a look at your equations to figure out which equation you think would be best based on what we already know, and what we found in parts A and B as well. Okay, so if we think about what is happening at this maximum height, that maximum height means the ball will not continue moving upward, right? Like it's the maximum height. It's not going to move higher than the maximum height. But that's important to actually like consciously realize what that means. Maximum height, the ball will not go above the maximum height, which means at that height, the velocity is momentarily 0. So if we take that to be our final velocity, 0, right before it starts coming back down, when it's changing direction, its velocity is momentarily 0. Now we know the initial velocity because that was given in the problem. We know the acceleration given in the problem. And we want to find that change in the height with respect to our 0 point. So once we kind of get that little clue, keep that in the back of your brain that maximum height means your final velocity is 0 at that point, then it becomes much simpler to figure this problem out. So here in this first step, I've written out that same equation 6, where our final velocity is now 0. And this change in the height, again, is measured with respect to our reference point, which is 0. Like our railing is a height of 0 for our problem. Right, so here we're simplifying that equation. And we want to solve for y1, the height at that moment. Right, so we can rearrange this equation to get this version of it, plug in our numbers. Remember to square the velocity. And we get a height of 11.5 meters. So that is the maximum height that this ball will reach. Now, if you want to know what time that will happen, again, there are lots of equations that use time. Figure out which one works best with the variables that we know and are given. So in this case, I'm just using this equation, right? Final velocity equals initial velocity plus negative g times time. Again, our initial velocity is 15, g is 9.8, and our final velocity at the top, again, is 0. So we're solving for time, and we get a time of 1.53 seconds. No worries, Kevin. Glad you're joining us. Okay. Do you guys have any questions about this part? Oh, Nolan. Hey, Nolan. That makes sense. Okay. Any questions about part C? Okie dokie. I think there's one more part that we're going to go through. Part D, find the acceleration of the ball when it is at its maximum height. Right, we just found the maximum height to be 11.5 meters. Now we want to know what the acceleration of the ball is. So remember, we said that at this maximum height, the velocity of the ball is momentarily 0. It's changing from upward to downward, so from positive to negative. And on a number line, when something passes from positive side to the negative side, it has to pass through 0. So we know at that moment, the velocity of the ball is instantaneously 0. What is its acceleration though? And this question, again, often trips students up because they think, well, if the velocity is 0, then the acceleration also has to be 0. But if the acceleration were 0, that would mean the velocity of the ball never changes. So it would just stay at 0 indefinitely. And that would mean that the ball is literally just hovering there in the air, never to move again. Clearly, that is not happening in our scenario here on Earth.
Miss Zamora,
Hello.
I'm really sorry I dozed off.
It's no worries. Glad you're here with us. So we know that the ball goes up and comes back down again. So even though the velocity of the ball is 0 at the top, the acceleration cannot be 0 in these physical terms that we're talking about. So everywhere in this problem, while it is in free fall, the acceleration is negative 9.8 meters per second squared, right? That acceleration due to gravity everywhere that the ball is in free fall, including at that maximum height. Okay, don't get tripped up by that. Professors like to ask that sort of question. All right, do you guys have any questions about this example as a whole? Okie dokie. Well, check out the slides. I'll post them on Canvas after class. So if you missed any part of the example, then make sure that you look through these steps that we took.
Oh, did I miss much?
We went through parts B, C, and D of the example problem.
Oh.
Okay, so there again, just clear orange box. Common misconception is that at the highest point, both the velocity and acceleration are 0, but that cannot be true because then the ball would never move again. Okay, so here is a problem. I want you to give it a try to just kind of set up this problem, figure out which equation you might pull out based on what you're given. So here's the example. A spacecraft landing on the moon has a downward velocity of 0.8 meters per second when it is 5 meters above the surface. The acceleration due to gravity on the moon is 1.6 meters per second squared. So if you want to know at what speed does it hit the ground, which of these equations, you could have more than one step, but which of these equations would be most helpful for you to use based on what you're given? So grab a piece of paper, jot down the variables that you are given in this problem statement, including some that might be kind of hidden in there. Like look for those key phrases that we talked about last week. Draw a sketch of the scenario, and again, try to figure out which equations would be the most helpful for solving this problem. So I'll give you a couple of minutes to think through that, and then we'll come back and talk through this together. All right, so now that you've had a little bit of time to think through this, maybe you haven't had enough time to solve the entire problem. That's totally fine. Again, we just want to sort of set up this problem to see how we do it. Let's talk about it. So here is my spacecraft. It is landing, so it's traveling downward with a velocity of 0.8 meters per second. So that means our velocity is negative 0.8 meters per second. I'm using the standard convention of up is positive, down is negative. It is at a height of 5 meters above the surface. So there are a couple of different ways that you could have done this, right? You could have set the ground to be your 0 point, and your your height would then be a positive 5 meters. Or you could set the height of your spacecraft to be your reference point, and then the ground would be at negative 5 meters. Either way is completely valid. So I used equation 6 based on what we're given, right? We know the initial velocity, we know the change in the height, we know the acceleration due to gravity on the moon. What we don't know is the final velocity. So equation 6 had everything that we needed, and I went with that one. So our initial velocity, negative 0.8 meters per second, square that, right? 2 times our acceleration due to gravity. Again, mine is negative because that is the coordinate system that I chose. And a change in height of negative 5 meters, again, based on the coordinate system that I chose. Okay, so that gives us, when we take the square root, that gives us 4.08 meters per second. Now, this is a positive answer that my calculator spit out at me. But if we look at the scenario and what is happening here, this spacecraft is moving downward. So based on my own choice of coordinate system, the velocity should be negative, right? Remember, in the previous example, we had 2 answers that ended up being, what was it, 127 meters squared per second squared. When you take the square root of that, you get 2 roots, a positive root and the negative root. Your calculator probably just gives you the positive root. But in this case, it would be the negative one that we want to show us that the velocity is downward. Okay, so now follow-up question with that. You should have your sketch already drawn, your variables list already made. Figure out which equation would be best suited for this problem. How long does it take to land? Take just a couple of seconds, look through that list of equations. Which one do you think would be most helpful in this case? All right, let's talk about it. Again, here's my sketch. We know our final velocity just before it hits the ground is negative 4.08 meters per second. So there are quite a few equations, as you saw, that involve time in some way. I chose this one because it seemed the most simple to me. So our final velocity equals initial velocity plus acceleration times time. Time is what we're looking for, so I rearranged this equation to get time by itself and ended up here. Our final velocity was negative 4.08 meters per second. Our initial velocity was negative 0.8 meters per second. And that acceleration is negative 1.6 meters per second squared. So that gives us a time of 2.05 seconds. So that would be how long it takes to land going that 5-meter distance. Okay. So now that we have a little bit of experience using these kinematic equations, applying them to free fall scenarios, we can extend these to more than just one dimension. So now we won't be looking at just horizontal motion or just vertical motion. We will combine them together, right? So this would be just just horizontal motion, right? That would be vertical motion. And here we have the two combined. Right? So that cat, as he's being thrown onto the bed, is both moving sideways and up and down through the air. That is our projectile motion, combining horizontal and vertical at the same time. Woo! Now, I don't condone throwing cats for these experiments, but I mean, you know your cat, so whatever. What hits the ground first? So here, if we have a ball that is dropped from 1 meter high at the same time that another ball is fired horizontally at 3 meters per second from 1 meter high, which one hits the ground first? There's a question in the chat. Do I have a cat? No, but I grew up with cats and I didn't realize until I came to college and was away from them that I'm actually allergic to cats. I have a dog now. His name is Toast. Okay, so some of you, if you guys watched Mythbusters, you may have seen they did this kind of myth busting experiment based on this. And I have video links to it on the next slide, I believe. For the sake of time, we can't actually go through and watch it, but those links are there for you if you want to see them actually kind of go through the steps of this experiment and what they did there. So just kind of think through this, get an answer in your head, right? A ball. So we have a ball that's being dropped and we're launching another ball horizontally from the same height. Which one is going to hit the ground first? Is it the dropped ball, the fired ball, simultaneous? We don't have enough information, or neither one will hit the ground and they'll just both fly off into space forever. Have an answer in your mind. Here are those video links that I'm just kind of casually passing off to you to look at in your free time. And our answer here is that they are simultaneous. For some reason, this just blows a lot of people's minds that these two balls, even though one is like traveling horizontally significantly faster than the other one, they will still hit the ground at the same time, right? So keep in mind here too, that in physics 1, we are always talking about the idealized case. So a lot of time we'll ignore friction, we'll ignore air resistance, all those things. We're just thinking about the ideal case. And yes.
They're simultaneous because of the acceleration due to gravity.
That's
and
right.
and like
gravity is acting on them both the same way, right? As soon as they leave the hand or the gun or whatever it's being launched from, gravity is the only thing that's acting on them, and it's acting on them in the same way, right? Pulling both of them down at negative 9.8 meters per second squared. And so they will end up hitting the ground at the same time. So that means that x, our horizontal motion, does not care at all about our vertical motion, our y motion. So those two motions are not related to each other. They are independent of each other, right? And that's why it's really important as we make lists of our variables and what we're given in problems, we have to pay attention to what direction we're talking about, right? If we're given an initial velocity, is that a horizontal velocity? Is that a vertical velocity? We cannot combine the two things together. We cannot have x's and y's in the same equation. That's two completely different things, independent of each other. So we'll take our old equations, old, I mean, we've had them for like 5 days, our old equations, and rewrite them as new equations. But you'll notice they are the same. It's just that we have a separate set for our x direction and our y direction. Otherwise, the variables are basically the same, right? We have velocities, accelerations, times, changes in position. But most of the variables you'll see will have a subscript x or a subscript y, except for time, right? Time is the only thing that is the same, the linking variable between these two directions, right? Because if you're throwing a ball or like throwing a cat, that cat doesn't land at a different time based on its horizontal motion than its vertical motion, right? The cat only lands once, unless it's bouncing, but that's something completely different, right? It only lands at one time. And so time for horizontal motion and vertical motion for a particular object is the same. So that's our linking variable. And that is an important thing to know, that time links both directions together. Okay, so as we go from here, all of the future examples that we do, we'll treat our horizontal motion as completely separate from our vertical motion, except for that variable time. Okay, so quick flashback to trig from, what was that, like our first week together? Figuring out our sine, cosine, tangent, all of those identities, what that means, how we get them from triangles. That is now particularly relevant for projectile motion, because we're not just dealing with falling straight down or moving straight across. Now we are being launched at angles, right? So angles are important here. Trig functions are important here. So these are pulled from our definition slide, the SOHCAHTOA slide from that previous chapter 1 PowerPoint. But these equations are also going to come into play. So I just rewrote them again here for you. Okay. But now, instead of just leaving it in terms of like generic vector A, we're dealing with specific vectors like velocity. So we'll replace the A, generic capital A, with velocity. Right? The equation is the same except for that. And I have it separated into horizontal component and vertical component, right? Because this velocity vector has both components. We need to look at both of those separately because one is vertical motion and the other is horizontal motion.
I have a question.
Yes.
What is the n plus x or like the n plus y? Is that where you put like your numbers?
No, so this just says this is in the positive x direction and this equation is in the positive y direction.
Okay. Okay.
Okay. Good question.
Well, do we use different trig functions for the other coordinate or the other quadrants?
So the trig function that you use is based on how the angle is defined, right? So here in this case, we're looking at this angle. And remember, the cosine of the angle is that hypotenuse of the triangle and the adjacent side of the triangle, right? Those are the two that factor in. So since our angle is here, this component of the velocity, the x component, would take use of the cosine function. If, however, for some reason we set our angle to be this internal angle instead, then our x component of that would no longer be adjacent to the angle, it would be opposite the angle. So in that case, we would use the sine because that
Everything would be in reverse.
hypotenuse. Yeah, so don't get too comfortable with this always being true. It depends on the particular scenario. The thing that is always true is how those trig functions are defined, right? Cosine is adjacent over hypotenuse. Sine is opposite side over hypotenuse. And tangent is opposite over adjacent. Okay, so yeah, now that we've started adding in angles and trigs, things get a little bit trickier. But I have full confidence in you. Okay. So here we have, not really an example problem, just a question to think through. Okay. I throw a ball at an upwards angle. What is the acceleration of that ball in x and y after it leaves my hands? So we're going to assume that positive x direction is to the right and positive y direction is up. Okay, so I'm throwing a ball like maybe across the room to my friend, throwing it up so that it arches up and then my friend can catch it. What is the acceleration in the x direction and what is the acceleration in the y direction? Take a second, think through this, come up with your answer, and then we'll talk through it. Okay, so remember what gravity is and what gravity does and what direction gravity acts in. What direction does it pull us?
I say it has to be D.
Okay, good guess. What direction does gravity pull us? Well, down, right? Gravity does not pull us sideways along the surface of the earth. Okay. Which means that gravity, our acceleration due to gravity, is just a vertical thing, a vertical quantity. Okay. Horizontally, as soon as that ball leaves my hand, there is no other force acting on it. Again, because we're ignoring things like air resistance and drag and all of those things. This is the ideal case. So as soon as it leaves my hand, nothing else is like pushing it more sideways or pulling it more sideways. There's no magnetism, nothing like that. It's nothing like that, right? So that means that our answer here is D. The acceleration in the x direction is 0. If there's nothing to change the velocity of the ball as soon as it leaves my hand horizontally, then the acceleration is 0 horizontally. Now, as soon as the ball leaves my hand, gravity is pulling on it downward, that's vertically. So there is an acceleration vertically of negative 9.8 meters per second squared. But this tells us that an object can have a different acceleration in each direction. So once again, acceleration is not something that links the two sets of equations together, because you can have a different acceleration horizontally than you do vertically. Just like you can have a different velocity horizontally that you do vertically. Okay. So do you guys have any questions up to this point? So far, it's all kind like this new idea of projectile motion has all been sort of conceptual. Starting tomorrow, we are going to be applying these equations that we just talked about in actual scenarios, thinking through how we can solve these projectile motion type problems, how we can extend that into 3 dimensions as well, if that's necessary. But these example problems can get a little complicated and a little long. And so we're gonna stop here for today, just because I don't want to have to like finish in the middle of an example like we did last time. So I know I'm letting you guys out a bit early today. It's not because I don't love you. It's because I don't want to have to stop in the middle of things once we get to these more complicated examples. So if you guys don't have any questions about today, then you are welcome to sign off. Have a great day, and I will see you guys tomorrow. But be ready, bring your calculator, bring a pencil and paper, because we're going to dive into these advanced projectile motion problems tomorrow. Have a great day, guys.
You too. Thank you very much.